Sir, good evening, sir. Sandeep, did ma'am register? Ma'am didn't get mail, it seems. Hello? Hello? Hello?
Ma'am.
Sandeep, ma'am did not receive the training program mail, it seems. Did she register?
Ma'am registered, ma'am.
Acha.
Gmail, ma'am.
Yeah, acha, through Gmail, la?
Yeah.
Gmail only.
Personal Gmail, ma'am.
Can you share any other link where she can join directly? Sandeep? Sandeep, can you add Radha ma'am to the panelist? She's there. She's already there. R. Radha. With the name R. Radha R. Yeah. Ma'am,
Yes, Rekha, am I joined now? But I'm not able to see the sharing option here. Hmm.
ma'am, sharing option we will provide, ma'am, in the 2-3 minutes we will provide.
Yeah, sure.
Yeah. Shall we start, ma'am?
Yeah, we can start.
Yeah.
Am I audible?
Yeah,
Rachel?
you're audible, ma'am. Perfect.
Yes.
Yeah.
Thank
Ma'am, we'll wait for another 2 more minutes, then we'll start.
Okay, sir. Ma'am, 2 more minutes. The participants are
you,
joining.
ma'am. Sure, sure.
Okay. Okay.
Ma'am, shall we start?
Yes.
Ma'am?
Yes, sir. Good evening, participants and the guest speaker. A warm welcome to you for 2-week faculty developed program on a holistic approach for sustainable and smart agriculture using AI and deep learning techniques. Right now, we have Dr. Radha Madam. So I request Shrikar to introduce Radha Madam to the participants so that we can move on with the session.
Good evening, everyone. Today we have with us Dr. Radha. Dr. Radha is working as an associate professor in School of Computer Science and Engineering. She has around 20 years of teaching experience. She has done her PhD from Anna University and is a university rank holder of Anna University for her PG. Her research interests include wireless networks and IoT. She has published around 15 research papers in various SEI and Scopus journals. She has completed 2 funded projects under AICTE, RPS, and TNSE SD. Now I request Dr. Radha to please take over the session.
Yeah.
Thank you,
Thank
Shri.
you. Yeah.
Sandeep, can you give presenter option to ma'am? Yeah. Ma'am, now the presenter option is given to you, ma'am. You can share your desktop.
Yeah.
Yeah.
Yes, right, ma'am. Yeah, thank you. Thank you very much for the nice introduction. Let me share my screen. Yeah, is the screen visible?
Yes, ma'am. It's visible, ma'am.
Yes. Okay. So, good evening, everyone. So, I'm here to deliver a lecture on IoT driven smart agriculture. And the outline of the presentation goes like this. I'm just going to give a very short introduction to smart agriculture and IoT. Then I will be concentrating on the various layers of IoT architecture, namely a data acquisition layer, transmission layer, and data storage and analytics. Then finally, I'll be presenting the security challenges in IoT for smart agriculture. Then the current work that I am doing under our Institute for Smart Agriculture will be presented finally. This is the outline of the presentation. And see, if we look at the generations of agriculture, we are in agriculture 4.0 now. So it has brought revolutionary changes in our in the world, agriculture 4.0. So starting from agriculture 1.0, like in our in olden days, people used animals for farming purpose mainly, and the disadvantage was the inefficiency in the operation inefficiency in handling, and utilization of large amount of land. And in agriculture 2.0, we started using more mechanized equipments like tractors. And again, the disadvantage was low utilization of the lands and inefficiency in the production. And agriculture 3.0 is about developing automatic agriculture. Again, it is with respect to the mechanical devices, but it does not have intelligence in it. And agriculture 4.0 now has brought a huge amount of intelligence in agriculture with the help of artificial intelligence, IoT, machine learning, and big data analytics. And it mainly concentrates on improving the efficiency of the production. And the types of, if we look at the types of the agriculture, there are three types of agriculture, namely precision agriculture, facility agriculture, and order agriculture. So in precision agriculture, the spatial and temporal characteristics of the land or of the environment changes, right? That should be considered in mind, and accordingly, the land should be treated, or the crops must be treated, and resource should be utilized according to the varying characteristics of the agriculture land. And it mainly, the objective of precision agriculture is to improve the utilization of the land, and to improve the resources management, the management of the resources, and improving the production and improving the quality of the food. These are all the main objectives of precision agriculture. And if we look at the facility agriculture, it is done, and precision agriculture is mostly done in the outdoor environment. What normally our farmers do comes under precision agriculture. It is otherwise called field agriculture, and it is large scale and mostly both in rural and urban environment. This is done. This is being done by the farmers. And if we consider facility agriculture, mostly facility agriculture is done under closed environment. Means the weather or climate conditions does not affect the facility agriculture, and it is maintained by human. The environment and the environment condition is maintained by the human. And the objective of this facility agriculture is to shorten the production cycle of the plants and to improve the production efficiency. That is the main objective of facility agriculture, and it is basically an industrial model. And order agriculture is like the demand for the agriculture is outsourced in advance before starting the agriculture itself. It is the demand in terms of the economy. It is outsourced and then it goes. It is purely a business model. It is also done under closed environment. And if you look at the order agriculture, it is mainly it will be maintained in a very good manner, and it is like a plant factory. It is otherwise called plant factory. And green house is an example for facility agriculture. So whatever may be the type of the agriculture, we need to treat the field and the crops based on its characteristics. For that, the data acquisition data needs to be collected from the crops and from the agriculture land and also from the environment, and it should be treated accordingly. So WSN, or the wireless sensor network, and IoT plays a huge role in all the three types of agriculture. It may be wireless sensor network, or the information can be collected through satellite, or it could be done using mobile telephone network also. But wireless sensor network and IoT plays a very huge role in all the three types of agriculture. And what is IoT? We all of us know, like IoT, it is a system to collect the data, store it, process and analyze it, so that we will be able to predict something, and we will be able to we'll be able to improve the quality of the agriculture in a very good manner. And it comprises of multiple things connected to the internet, and each thing is otherwise, it could be a sensor or actuator or any electronic device which has unique identity. And usually identity will be with respect, it is IPv6 is used for identifying the individual things in the computer, because IPv4 is already saturated, and we started using IP version 6. So each device in the IoT will be given a unique IPv6 address, and IoT allows all the things to communicate and exchange the data. And what is the purpose of collecting data and what is the purpose of analyzing it? Ultimately, we should be able to improve the profit from the agriculture, and we should be able to produce a quality food to the consumers, right? So IoT helps in doing all this. And we know the number of IoT devices connected to the internet in 2025 will be around 75 billion. It is already crossed, it is already more than the world population, and each one of us have at least 2 or 3 devices connected to the internet. So the data generated from the IoT is very huge, and it leads to knowledge mining and prediction. Right? And if we look at the moving on to the IoT architecture, there are multiple view in this. Actually, there are many different types of architectures. 3-layer architecture or 4-layer or 7-layer architecture. And for agriculture, for smart agriculture, the 3-layer architecture suits very good. And if you look at the first layer, is the perception layer, where the end devices like sensors, actuators are connected. The end node or the sensor nodes form the perception layer, because from these devices only we are going to collect the data. And the second layer is the backbone of IoT, which is the transmission layer. Whatever the data collected from the sensors need to be analyzed, stored, and then analyzed. The analysis could be done either in the edge or in the cloud or in the fog, but we need connectivity for communicating this data to the end, like to the end application, right? It could be edge or cloud or fog. So there comes the transmission layer, and there are multiple the protocols used for IoT. The existing protocols which is used for connecting computers are not suitable for IoT, because IoT is energy constrained. It is the devices are very small in size, and it can consume only a very less amount of energy because it is battery operated, and it is computationally constrained. Considering all these, there are many protocols developed exclusively for IoT devices. It forms the transmission layer, and the next layer is about the data storage and data analysis layer. This is about applying analytics or machine learning and deep learning or data mining on the data retrieved from the field, and controlling the equipment or controlling the actuators which are present in the agriculture land could also be initiated from this part, from the application layer. So the application could be either the edge device or the cloud device, which is going to control the actuators. So this is the architecture of IoT, the 3-layer architecture. And I'm going to concentrate on the first 2 layers. I hope the data analytics, machine learning, and deep learning is already covered, and it's being covered by multiple resource persons. I'm planning to concentrate on perception layer and transmission layer with respect to IoT architecture. And like data acquisition in smart agriculture, or we can say data collection from the smart agriculture, is mainly done with the help of agricultural sensors. So the agricultural sensors can collect both environmental condition and also crop growth related information, and the information is going to be sent to the cloud or to the internet, right? And like it could be the sensors could be present from can be part of the smart irrigation system, like for monitoring the water levels and the efficiency and the water flow, and even the climate sensors can be used. And we can use multiple sensors for sensing the soil nutrients, like the macronutrients of the soil, which is very much important for finding the health of the soil. The nitrogen, phosphorus, and potassium, no, it is acting as the macronutrient for the soil. So there are sensors available for reading these values, and soil temperature, environment temperature, humidity. There are sensors present for retrieving all these or for measuring all these values. And we can also monitor livestock like cattle and poultry farm can be monitored using smart sensors like the nanothermal sensor, temperature sensor, can be used for monitoring the health of the animals which are present in the livestock farms. And all these functions are generally performed by the sensors. And every sensor which is present, whatever may be the type of the sensor, it is going to sense the value, and we need a microcontroller and a communication module for communicating the sensed value to the network or to the internet. So sensors is the main source for collecting data from the agriculture land. And the second source is the agricultural satellites. Like the geo or LEO satellites can be used for area estimation of the agriculture land, and the growth of the crop can be monitored from the LEO satellite, and the pest information monitoring, and the yield mapping, vegetation index, and canopy cover. All these can be found using even the satellite remote sensing. And grassland vegetation monitoring can also be done using the satellite. So satellite is the second source for collecting the data. And the third source is like crowd sensing. Crowd sensing is nothing but, see, each one of us, like let it be farmers or the end users, we have mobile phone. And through mobile phone, the information can be shared and can be utilized for the for agriculture. Mainly the crowd sensing, like the sensors which are present in our mobile phone, are being used for intelligent transportation through Google Map, or for public security and environmental monitoring. But the application is limited for agriculture. So, it needs to be encouraged. Even crowd sensing can be used in smart agriculture for collecting the data from the farmers. So, for example, there is a mobile information system proposed in a research paper, which will be a portal for the farmers to report about the pest information and their disease information of their land, so that it will be helpful for the nearby farmers. So the mobile based information can also play a huge role in terms of data acquisition. And the next information system is plant phenotype information system. Like the plant phenotype is nothing but getting information about the entire plant, its image, and its entire the parts of the plant needs to be analyzed. So that is called the phenotype information. That could be retrieved using UAVs and agricultural robot. And even satellite can be used for getting the plant phenotype information. This will be very much helpful. Normally, the plant phenotype information is like the massive images of the plants, like how much it has grown, the growth status, and the videos, the surveillance video, and text data can be collected through this UAVs, drones, robot, and satellite, and it can be used as the data acquisition tool. And whatever we have seen, that is the sensors, crowd sensing, satellite, and even plant phenotype information, are acting as the data acquisition tools for smart agriculture. And like after collecting these data, like it will be sent to the cloud for analytics. And finally, cloud or the edge device will be controlling the agricultural equipments. Like it needs to be controlled, right? Otherwise, there won't be any outcome. Like in order to maintain the land or improve the efficiency, the actuators which are present in the agricultural land can be controlled. It is called actuators. So these sensors and actuators are the main components of the perception layer in the IoT architecture. And like if you consider a greenhouse, like the actuators could be like the irrigation device. Since the greenhouse is fully under the closed environment, it is going to be fully controlled by the human, irrespective of the climate or the weather condition, right? So there will be much more actuators present in greenhouse and plant agriculture than precision agriculture. Right, the lighting should be controlled, and air circulation in the greenhouse and the carbon dioxide and oxygen level needs to be monitored. and the disease control can be monitored. All these can be done with the help of actuators. And this forms the data acquisition. And if we look at the applications of smart sensors, like we know earlier, the soil health monitoring, like using the NPK, the macronutrients and micronutrient sensor, then moisture sensor, then soil compaction sensor. All these are the sensors, the soil fertility sensor. These are all the sensors that can be used under soil health monitoring. And irrigation monitoring. Under irrigation system, we have multiple sensors for monitoring the flow level of the water, and the leak detection and climate can be read using the sensors. And leaf the wetness can be read using leaf wetness sensors. And there are multiple sensors present under each application area, which will be acting as the data acquisition layer. And whatever may be the type of the sensor, the architecture should contain the sensor. The sensor module should have a microcontroller with memory, a limited amount of memory, then analog to digital converter, and there should be a communication module present, and it could be either battery operated or continuous power supply can be given. So these are all the basic units in any sensor node. Like it should be present for any type of sensor. And like if we look at drones, drones play a huge role. Drones and agriculture robot play a huge role in agriculture 4.0 generation, 4.0 generation. So normally drones are equipped with multiple sensors, like for monitoring the environment, and also for reading the environment. 3D cameras, thermal cameras, and multispectral cameras can be attached to the drones. And the drone operations are normally like a drone can act as either a sensor and also an actuator. So camera is also a sensor, and the weather sensors, all these are sensors. It can also act as an actuator by spraying the fertilizer, by sprinkling water. These can also be done using a drone. So drone can also act as a actuator. And the operations that can be done using drones are like there are many health indicators can be measured, and the vegetation density, pesticide prospecting, that is analyzing the pesticides used in the agriculture land and managing it. In the same way, fertilizer management, canopy cover mapping, like finding out the ratio of the trees with respect to the land, the vertical trees with respect to the land, and field prediction. All these are some of the applications that could be executed on the drone. And the disadvantage or the challenges while using drones are drones normally fly for a short amount of time. It also operates on battery, right? So it can run maximum for an hour or two. So that flying time is very less, and the flying path should be either a predefined path or it should be manually operated. If it is a predefined path, there are so many challenges in identifying the obstacles in the environment and accordingly taking the path. So all these are challenges, and it is very expensive when we try to use multiple 3D camera and thermal camera in the drone. It becomes very expensive, and there are some laws or policies that we need to follow while using drone. And the climate also impacts the drone operation. We need to check the climatic condition, and mainly like when we embed the cameras in the drone, like we need to convey, like we cannot, it cannot have an artificial intelligence board or something. Like it can be a microcontroller or microprocessor. Even now AI based boards are available, but it is very difficult to execute a deep learning of executing or finding out, detecting object or using a drone, because it takes time. The capability of the processor which is present in the drone is very limited. So we need to send the images or the videos to the server, to the edge server, and then the deep learning model should be executed in the edge server only. In that case, no, sending the images for that, when we use Wi-Fi or when we use cellular communication, It consumes lots of amount of energy. And the IoT communication technology is meant for transmitting a limited amount of information. So in terms of communication also, there are a lot of challenges while using drones. And as I said, like normally drones are used for harvesting the tomatoes here in this diagram, and also for spraying the fertilizers, and for finding the vegetation index of mapping the seed mapping can be done using a drone, and sensing can also be done. So basically, drones, the multi-rotor drone, can be acting as a sensor and also an actuator. And agriculture robot is another main component for agriculture 4.0. It also can execute all computer vision related operations. Like here, if you see, no, it is also helpful for harvesting the crops. And no, it is very difficult to get. It is very difficult to get the phenotype information of the plant using drone. Because no, you will not be able to get the image of the entire plant, and all for that robo will be very much helpful, right? Since it is going to be in the land, it will be very much helpful for finding out the pest infestation, and livestock applications are also used in the robot. And if you see this robo, which is shown here, has two tanks, one for spraying the water, the other one is for spraying the fertilizer. So this is just an example. So these are all the data acquisition and actuators which are helpful in the IoT device, like smart agriculture. And when we consider, okay, how to arrange these sensors. So depending on the area of the agriculture land, we need to decide what level of IoT should be used in the agriculture land, right? There are 6 levels of IoT. The complexity increases from level 1 to 6. So like if we consider level 1, like the level 1 is like if you consider the components of the device here, there are two components, local and cloud. We know IoT is about connecting the things to the internet, right? The internet could be like, it could be a cloud server or a server which is web server which is present in our organization, or it could be an edge server again, which is in turn connected to the cloud, right? So these two are the components that we have, local and cloud. And in the local, like if you consider the device, like the device is nothing but here the sensor and also the microcontroller or microprocessor, which is nothing but the device. And this device needs some resource. Like if you consider Raspberry Pi, for the Raspberry Pi device, the Raspbian OS could be the resource. And for Arduino, the C++ based framework which is built on Arduino, is nothing but the resource. So resource is nothing but the software which will be helpful for interacting with the hardware, right? And the controller service is the application that we do write in the device. It could be a Python application, or a Node JavaScript based application, or C based Arduino application. Whatever may be the application that we write, it is going to just get the data, collect the data from the device, and write it to the database. Again, in level 1, the database is present in the local device itself, like in the Raspberry Pi, or or any microcontroller based board. A database could be there or it may not be there, right? When it needs to be connected with the internet, you can use REST or WebSocket services, like request response, a HTTP kind of model, for accessing this particular device. Because we must be able to access this application from anywhere in the internet, right? So you need a web service for getting connected to the device. So this is nothing but level 1. So we can say the home automation system is a very good example for IoT level 1. So here there is a microcontroller which is connected with the various devices at home, right? The lights, refrigerator, and all other devices could be connected and controlled in using a single application. But that application could be a web-based application, so that it can be controlled from the remote place also. But there is no analytics done here in the cloud. That is called IoT level 1. And in IoT level 2, like smart irrigation is a very good example for IoT level 2. Like for example, based on the humidity level and the temperature level of the soil, we need to operate the irrigation system, right? So for that, this IoT level 2 could be used. So again, here if you see the local application which is running in the microcontroller will be sensing the soil temperature and humidity, and accordingly it itself operates the valve like the irrigation system. So the decision is taken here in the local device itself. But again, for long-term scheduling of water and for long-term scheduling, you need to write this data, the data sensed from the soil to the cloud, and there could be some application which does a long-term scheduling. For example, if there is no water, if there is a scarcity of water, then if you have to buy water and do agriculture, then based on the past data which is present in the cloud, we can actually go for irrigation, like the amount of water that should be purchased, right? This is level 2. So in level 2, a little amount of analytics is done in the local and a little analytics is done in the cloud. This is IoT level 2. And in IoT level 3, most of the analytics will be done in the cloud. It means the server or the edge. It could be edge server also. It need not be a cloud server all the time. It could be a server which is present in our organization or edge server. Now, if you see tracking a package, for example, assume you have a very costly item or asset which is to be delivered to you. We need to monitor that asset. It is to be carried through some transport system. So it needs to be monitored using the accelerometer and gyroscope. So the continuous monitoring has to be done, right? So the monitoring can be done from the cloud. The vibration level of the transport and even the road damage, the traffic around that particular vehicle, all those can be monitored from the cloud and it can be controlled. The driver can be given information from the cloud about this. So this is called IoT level 3. Most of the analytics is done in the cloud. Every time, like maybe every 15 minutes or half an hour, we need to continuously send the vibration details or the traffic information to the cloud. So it's a huge amount of data is involved in this. So it is better to do it in the server instead of the local microcontroller. This is about level 3. So till level 3, only a single controller is being utilized, right? But like if you consider agriculture or we will have a lot of sensors across the land. So one microcontroller with a little amount of few sensors may not be sufficient. In that case, we have to go for multiple sensors connected with microcontrollers, right? So in that case, each microcontroller or each device is connected to the server, right? Each device is separately connected to the server here, and analytics could be done in the cloud or the server. Okay, so now there can be observer node which is present in the local location. It is only for observing the information. It is not going. This node is not going. It does not take any primary responsibility. Okay, so everything is done by the cloud, and the actuators which are connected with the controller can be controlled by the cloud device here. So the sound monitoring or noise monitoring is a very good example. If we want to monitor the noise level in a particular area of town, then you need to have multiple sensors across the entire town. And individually, each sensor has to be connected to the cloud and it needs to be analyzed in the server. This is about IoT level 4. There are multiple sensors. Each one is connected to the internet directly here. And the next one is forest fire detection. Like if you consider forest fire detection scenario, here also we need multiple sensors. But no, we cannot connect each sensor to the internet directly, right? Because the signal shortage may be there. Signal may not be available to all the sensors, right? So in the forest. In that case, one of the device could be acting as a controller. It is like it can act like the access point or the gateway can act as a controller, which will be connecting all other devices to the internet, right? So like all the individual devices are connected to the controller or coordinator. Coordinator in turn is connected to the cloud. So even here, the controlling and the analytics component is present in the server instead of the coordinator. It is present in the server, like the cloud server. The weather information is continuously sent here, and the coordinator can do only a very little analytics because it is also very limited in terms of energy. Most of the analytics is done by the server through REST or WebSocket communication. This is level 5. And here wireless sensor network comes into picture here in this case. And the network could be the Zigbee network or Bluetooth network, which is connected to the gateway. Gateway in turn is connected to the cloud, right? And the next one is weather monitoring. So for weather monitoring, here it is the very the highest complex system in IoT. So here there will be an edge and also the cloud. Edge, the centralized controller which is present before cloud. It could be a fog server or edge server, and like all these end devices are connected to the centralized controller. Centralized controller can do a limited task like in the edge itself. Because, for example, sometimes we may have to do some time sensitive, time critical decisions have to be made only in the edge because the latency is high in the cloud. The latency, like all the data has to be sent to the cloud, and cloud has to analyze and take decision, and then controlling could be very much time consuming. So the time critical applications could use the edge server that will be running in the centralized controller here. And centralized controller in turn is connected to the cloud. The permanent data storage is always done in the cloud for long-term analytics, right? For long-term prediction. Okay, these are all the 6 levels in IoT. So depending on the complexity of our project, we need to decide which level to go for. Okay, so like here, if you see in the weather monitoring system, the sensors that could be connected with the microcontroller could be wind, measuring the wind speed and direction, the radiation, solar radiation, temperature, and humidity, and even the barometric pressure and soil moisture, snow depth. All these sensors could be connected with each controller, and which in turn is connected to the centralized controller. That is the edge server, and edge server in turn is connected to cloud server, right? And this is about the data acquisition layer. Next, we move on to so in the data acquisition layer, we just saw what are the types of devices that could be used for collecting the data and how it could be arranged, how complex the system should be, like what level could be used from the IoT. That is what we just discussed in the data acquisition layer. And the next layer is transmission layer again. So which is the backbone, as I said. The data collected from the sensors or the satellite or the crowd sensing devices need to be transported, and most of the like IoT devices uses sensors, right, which are very limited in terms of energy. So we need exclusive protocols which are meant for saving the energy and also the reducing the computation. So these are all the technologies, the IoT technologies that are present for transmitting the information to the cloud. So Zigbee and then Wi-Fi. In Wi-Fi, we have multiple standards, multiple versions. Wi-Fi Halo is suitable for IoT. And then in Bluetooth, we have Bluetooth Low Energy and Bluetooth 5. And narrowband IoT, LoRa, Z-Wave, Sigfox. All these are the technologies developed for transmission. And like in IoT communication or the IoT communication protocols, the designed protocols, should consider all these properties of the sensors. Like it should be low cost. All the sensors are low cost. It means it has very limited computation power, and it runs on battery. The communication protocol should not drain the energy by continuously transmitting control information. So it should consider the long battery duration And high number of connections, it means a large amount of sensors should be connected with a particular, we should be able to connect large amount of sensors with a gateway. Then only we will be able to collect lots of data, right? So high number of connections. Then the bit rate is normally very less because we are interested in sending text data. The IoT communication protocols are not suitable for transmitting multimedia data, like no images continuously. But there is one exception, like Wi-Fi Halo can be used for transmitting images because the data rate supported is somewhat high. Okay, so but otherwise, all other communication protocols consider all these characteristics of the IoT sensors and it act accordingly. You cannot use either the Ethernet or the normal 802.11b or 3G, right? These protocols are meant for like laptops and mobile devices, which has a large amount of energy. But IoT devices are lacking in energy and power. So that should be considered by the protocols. And the latency is again relaxed latency. We need not we need not send continuous data with high data rate. Okay, and the architecture of the protocol should be very simple. And these are all the standardized IoT protocols. Only the data link layer protocols are very much different here. Like 802.15.4, the Zigbee standard, 8 Max standard. Then BLE, Bluetooth Low Energy, RFID and NFC are also like the part of IoT. And then Wi-Fi Halo. Then we also have NB IoT, all these. And if you see, the transport layer does not change here. Normally, like TCP and UDP are used as the transport layer protocol. And in the IP layer, right, in the network layer, there are two new protocols, like we can say the RPL protocol, routing protocol for low power lossy network. It is meant for IoT actually. And 6-flow PAN is also for IoT. Because I already told you, like each thing or each sensor connected to the internet should be uniquely identified, right? So that it can be controlled remotely. So while if we have to identify, we have to use IPv6 address because IPv6 address is not sufficient. So when we use IPv6 address, the length of the address itself is 128 bit. So but we know it is like it does not have huge computation power and the packet size should be very, very less. We cannot assign 128-bit address to the IoT sensors. So for that purpose, 6-flow PAN. Okay, IPv6 over low power wireless network. Okay, so the 6-flow PAN is an adaptation layer, like a thin layer in between data link layer and the network layer, which is for again for shortening the IPv6 address mainly. For header compression, the 6-flow PAN is used. And if you look at the application layer, the messaging protocol in the application layer is also different. Like HTTP is very rarely used in IoT. But otherwise, MQTT, AMQP, and XMPP and QoAP, all these are frequently used messaging protocols for IoT devices, messaging protocol or application layer protocol. And again, all these protocols supports application layer security. That is the transport layer security, SSL. Transport layer security is present for all these protocols, right? These are all the like the list of protocols that is going to be used. And when we consider the IoT communication protocols, I think I'll stop with this for 10 minutes the break, right? Rekha ma'am?
Yes, ma'am.
Yeah,
Okay, ma'am.
shall I stop here? Or
Yes, ma'am. We will continue again, start at 8 o'clock.
yeah, yes.
Right.
Yeah, let us
Participants,
have 10 minutes break.
yeah, you can take 10 minutes break and get back by 8 o'clock. We will continue the session.
Yes, ma'am, shall we start?
Yes, ma'am, please.
Yeah. Is it fine, ma'am? Is the volume fine?
Yeah, it's fine now, ma'am.
Okay. Fine. So next, we are just going to look at the IoT communication technologies, which is meant which are the data link layer protocols, especially data link layer protocols. As I said, the higher layer protocols do not change much. TCP, UDP, and IP are used as the higher layer protocols with few additions, right? But the data link layer protocol entirely changes here, right? So if we look at the distance in terms of distance, like Sigfox, LoRa, and NB-IoT gives us very good distance up to 10 to 15 kilometers. It means if we keep a gateway, LoRa gateway, or if you consider NB-IoT tower, it can cover sensors up to 15-20 kilometers range, right? So, like we will be thousands of sensors can be connected with the LoRa gateway, and it will be able to get data from the very large land, right? That is LoRa gateway in terms of like distance. And if you consider the data rate, the Sigfox or LoRa or NB-IoT gives you data rate in terms of kbps, right? In terms of kbps. And no, because most of the time we will be sending text data from the IoT sensors. It will be no temperature, humidity value, or some text data is normally communicated. So, like these protocols are suitable for low bitrate sensors only, right? And when you consider Zigbee, it has very limited distance, like up to 10 to 50 meters only. And Bluetooth low energy goes up to 100 meters now, like Bluetooth 5.0 goes up to 100 meters, and the data rate is up to 100 kbps. And when we consider IEEE 802.11 AH, which is otherwise called Halo, it is a new standard in IEEE 802.11. It is a Wi-Fi standard. It covers up to 1 kilometer, right? It means the access point can cover up to 1 kilometer. But presently, we are using 802.11b in at our home, right? It covers only 50 to 100 meters. But this halo is meant for IoT, so it means it covers up to 1 kilometer, and 8,000 devices can be connected with one gateway, right? So it means like in a field, in an organization, or in an agriculture field, which is of 1 kilometer radius, can be taken, and around 8,000 sensors can be floated, which comes under one gateway. Okay, so this is how the IoT communication technology. So only with the help of Halo, we can go for transmitting images, but not in a continuous manner, because most of the time, like it is low duty cycle. It means most of the time the sensors will be sleeping. The microcontroller turns on rarely only. So for transmitting multimedia data, IoT communication technologies are not suitable. But if you want to transmit image in a particular event, when a particular event happens, if you want to transmit an image, then you can go for Halo. Because the advantage of IoT communication protocols are they consume a very less energy only. No, the lifetime of the sensors can be up to 10 years or 5 years. But it is not so when we use Wi-Fi or a normal communication technology, which is meant for no, computer and mobile devices. Okay, this is about the IoT communication technology. And let me just know a brief about the IoT messaging protocols. Because this is also different from the traditional protocol. Like we have MQTT, AMQP, QoAP, then XMPP, QoAP, and HTTP. All these are the IoT based protocols. HTTP is rarely used. It is a request response model, right? And if you consider the type of communication between the end device and the network, network here means network server. Okay, so between end device and the network server, it may be the communication may be initiated either by the sensor or by the network sometimes, right? When the network wants to control the actuator, it has to initiate. When some event happens, that data has to be sent to the network server. In that case, end device triggers, right? End device has to initiate the communication. Sometimes both of them have to communicate with each other. Like it will be sending some request and network has to send some reply back. And sometimes they may have to communicate with each other simultaneously. Okay, so there are different types of communication possible in IoT. The first one is asynchronous COAP. It is also based on request response model, but here the response is asynchronous. The response need not be sent immediately. Once the request is sent from the client to the server, the request will be acknowledged by the server. Then after some time, whenever some condition is met, the server can send the response. So it need not be synchronous, it is asynchronous. And for sending streamed request and response, XMPP protocol and DDS protocols are normally used. Okay, so there will be a connection established, and then in between the connection establishment and termination, multiple messages can be exchanged. And this is very famous communication model for IoT, that is MQTT, COAP, and AMQP. So COAP can work both in request response model and a subscribe publish model. So it means there will be a broker or a server acting as a broker. So the client or the publishers are nothing but the sensors. So they will be publishing the data, right? And whomever has subscribed to that particular data will automatically receive the data from the broker, right? So here, the servers or the sensors do not know about each other, but the communication is entirely done through the broker, which is present in between. This is another popular communication model meant for IoT, and even in web it is used. The publish subscribe model is used in web applications also. This is about IoT messaging protocol. And next one is like IoT communication technology. Like I'm just going to give you only the overview of all the communication technologies. Like the first category is fixed and short range, which is up to 1 kilometer. And like for long range, it is up to 20 kilometers. In fixed range, we have RFID, Bluetooth. Bluetooth here means Bluetooth low energy and Bluetooth 5.0, and Zigbee, then Wi-Fi Halo, right? These are all the fixed or medium range communication technologies. And under long range, we have LoRa, which is very popular in India. LoRa and NB-IoT is very popular in India for long range wireless wide area network, right? It is like a wide area network. It is long range, it goes up to 20 kilometers. And again, if you see all the fixed and short range communication technologies uses ISM band. It is license free band. Anyone can utilize it without any cost, right? It is license free band. But 3GPP standards are, it is cellular communication based standards. So it works under licensed band. And all these LoRa, Sigfox, and RPMA comes under non-3GPP. It is long range, but again, it is license-free band. Okay, but it is proprietary. It is not owned by the government. It is proprietary organization. So Sigfox and RPMA is used in other countries, and LoRa is the most frequently used technology in India. Now, let us see RFID, how RFID can be helpful for agriculture. So before going into the case study, let us just see, we know there are two components in RFID, tag and reader. Right? The reader is the one which will be getting information from the tag. The RFID tags save some information. There are two types of RFID tags. It is nothing but a microchip connected with an antenna. It is stored with some information, and it is going to just emit the information whenever reader polls the tag. Okay, whenever reader polls the tag will be emitting the information which is kept in it, right? And it appeared very long back, and it comes along with, like, when we consider a scenario, like again, let me just tell you the difference between passive tag and active tag. Like passive tag does not have any battery. It operates by the RF energy emitted from the reader enables the passive tag, right? Whenever RF signal is emitted from the reader, the tag emits whatever information that it has, right? And it does not have any battery, and it is very short range. It works up to 3 meters or 5 meters only, and there can be hundreds of tags connected with one reader, and data is also very limited. You cannot transmit a multimedia data and all. 128-bit byte text data can be transmitted from passive tag, right? And active tag has its own battery. It has multiple other communication technology like Wi-Fi, and it can emit its own data since it is operated on battery, right? It is purely active, right? But again, the amount of information that can be emitted by the active tag is also very less, but the range is longer. Okay, so now like consider cattle monitoring application. Like if you see the components of this project are like we have animals need to be monitored from remote place. There is no herdsman required here, right? So in that case, assume the RFID tags are the collar tags, like the ear tags, which are available in the cattle, right? And then there should be a handheld reader which is present near the location. So it will be like continuously getting information from the tags, right? So the ID, the unique ID which is stored in the passive tag will be emitted when the reader polls the tags, right? And this reader can be connected with the base station, the GSM enabled handheld reader. Information can be sent to the base station, and from there the herdsman who is present remotely from his mobile phone, he will be able to monitor where are the cattle, whether they are within the range. The GPS location of the each cattle can be viewed by the herdsman. Okay, so this is how it works. It is enabled with the GPS. The location information and the cattle information is retrieved through the reader. Okay, this is one case study. And next is Bluetooth. Bluetooth has the recent version of Bluetooth is Bluetooth 5.0, that's 5.0. It is low power wireless technology again. Whatever the Bluetooth that we use in our car or in our headphones uses Bluetooth 3.0, right? It is meant for multimedia transfer. It is not meant for IoT. There we assume that the power is available, right? But for IoT, the Bluetooth 3.0 does not help. But Bluetooth low energy and Bluetooth 5.0 is very much helpful for IoT, right? And the topology that can be used in the Bluetooth are the star topology. One device, there can be only one master, and there can be 8 slaves, active slaves. And these are all parked slaves, or we can say it is sleeping slaves within the range, right? There can be 8 active slaves which will be communicating with the Bluetooth coordinator, that is the master. And here for Bluetooth 3.0, the data rate is 1 Mbps. But for Bluetooth 4 and Bluetooth 5.0, it is very less. It will be in terms of kbps. But Bluetooth low energy gives you very good battery life. It will be for years together, right? It is meant for IoT sensors, can be BLE enabled sensors, right? The microcontroller can be BLE enabled. And the Bluetooth 5, the recent version is 4 times the distance of Bluetooth 4. It means it covers up to 150 meters. Practically, it covers up to 100 meters and 2 times the speed. And the broadcasting message capacity is also high for Bluetooth low energy. Okay, but the latency and battery life is very good for Bluetooth low energy. Now, when we consider a case study for Bluetooth low energy, assume we just want to trace the food system, right? The agri-food traceability system. We want to trace how the supply is, right? So when the food products are loaded, right? When it is loaded, assume each box in the each food product or each box is having the BLE enabled tag or BLE enabled sensor. which is meant for monitoring the quality of the food. There are many biogas sensors which can sense the quality of the food, whether it is good, and even the count can be received using the BLE gateway. Now, when it is loaded into the vehicle, and when the vehicle goes out, it is there is a beacon concept. We don't need to pair the BLE beacon with the BLE enabled sensors, right? So the beacon, it will automatically, when it emits the beacons which are present in the boxes, will be able to send the data to the gateway automatically. Like a normal Bluetooth, we don't need to pair the slave and the master here, right? And then when it is unloaded again in the warehouse, again the sensor which is present in the box, the beacon which is present in the box will be searching for the master node, and it will be emitting the sensed data will be sent to the gateway which is present. So now if you see the gateway which is present here, or Bluetooth low energy enabled gateway, which is in turn again connected to the Wi-Fi gateway. Because you cannot connect the Bluetooth gateway directly to the internet. You need to connect it to the another dual antenna device, which has both dual stack, both Wi-Fi and Bluetooth. So from the Bluetooth gateway, the data is sent to the Wi-Fi gateway, and from Wi-Fi gateway, it is sent to the cloud database. And the owner will be able to see from his mobile phone, he will be able to monitor the quality of the food and the count of the boxes. All those can be monitored from the smartphone app here. And since the range is the Bluetooth low energy, it goes up to in Bluetooth 4, it is less. Again 25 to 30 meters, but for Bluetooth 5 it goes up to 100 meters. Okay, so this is a case study which uses BLE technology, and this is how the traceability system works. Now if you look at the sensor node which is present in the boxes, it will be searching for the coordinator node, and if the coordinator node is present, right, then it will be able to broadcast. The sensors will be turned on, and from the sensors the data will be transmitted, right? Data transmission is done to the coordinator node, and the coordinator node will be sending it to the Wi-Fi gateway. And if the coordinator is not found, and it goes for the sleep mode, right? This is how the traceability system uses BLE sensor. Again, Zigbee. So Zigbee works in multiple topologies, like star topology. We know one gateway and multiple end devices, or it could be in a tree topology like this, and mesh topology can also be there. There are three types of devices. Like the Zigbee coordinator is the one which is going to consolidate all the data and send it to the the internet, right? The wired internet through wired connection, or through wireless connection. And then Zigbee routers are the fully functional devices which will always be on. The FFD which are present in the Zigbee network will be on all the time. And the RFDR is nothing but the end device, Zigbee end device, the green color circles, or the end devices, right? It cannot be always on. It will be in the sleeping state most of the time. And through the fully functional devices, that is routers, the information reaches the coordinator, and from there it reaches the internet. Again, the MAC protocol that is used in Zigbee is 802.15.4. It also supports in kbps only, right? And the number of it is very popular in agriculture. Most of the agriculture fields makes use of the short range agriculture field makes use of Zigbee because of the long, huge number of connections. 65,000 nodes can be connected in one network. That is the number of connections that can be made, right? So this is about Zigbee, and this is one form monitoring system where sensors and actuators assume like the farm has to be monitored for the diseases and the pest, and even for the weed. Okay, so there are multiple sensors present across the entire field, like gas sensor, soil sensor, rain sensor, and wind speed sensor. And these sensors have to be connected with the controller, right? The microcontroller, which is called collector here, right? And the collector is Zigbee enabled. And this collector sends the data to the router. Router in turn sends the data to the gateway, right? The wireless gateway, which is also enabled with GSM. From there, it goes to the internet and a cloud. And from the cloud or from the server, we will be able to control the actuators, like switching on the motors and the PMC can be done through the controllers. So there are two types of control microcontroller here. One is collector, the other one is controller. Controller is for actuators, for connecting the actuator, and collector is for the sensors. Okay, so here the Zigbee protocol is used. And Wi-Fi Halo is, it has a data rate up to 1 to 10 Mbps. Still, it consumes the energy consumption is very less. So image can be transmitted based on some events using Wi-Fi Halo, not in a continuous manner. If you want to know, based on a particular condition, if you want to transmit an image from the drone or from the robo or from the surveillance camera, you can use Wi-Fi Halo. Wi-Fi Halo. Otherwise, like if you want to continuously transmit the data all the time, we cannot go for Halo. We need to depend on Wi-Fi, which will again consume energy. If there is a continuous power supply for the controller or the processor, then we can go for Wi-Fi. If it is energy limited, then better to go for Halo. Okay. So it is a new standard which was released in the year 2018. It is available as product in other countries. It also runs on license-free band. It is longer than Bluetooth or Zigbee. It covers up to 1 kilometer and up to 10 Mbps, right? But in India, we don't have these products. These products are but it works in license-free band. We can try to use these for transmitting image data, right? And if you see the battery life, it will be for no years. It will be for 5 to 10 years. And the use case for Wi-Fi Halo is assume we have you need to monitor the pest animals. We know there are many pest animals like monkeys, elephant also damages agriculture crops, right? There are huge amount of loss for the agricultural farmers because of the pest animals. So we may have some trap in the field, right? The farmers may keep some trap. So if you use Halo, you will be able to identify whether it is a pest animal or some other thing from a remote place. So for that, the Halo can be used here. Now, if the pest animal here it is boar, if the boar is trapped, then from your home you will be able to identify what is trapped here, and you will be able to take action accordingly. Okay, but since it supports a huge data rate that is up to 10 Mbps, you can go for transmitting the image, but you cannot do it in other IoT communication technology. And the very popular the communication technology is LoRa, which is expanded as long range wide area network, long range low power wide area network. Depending on the gateway, it covers up to 15 or 20 kilometers, and it uses chip spread spectrum technology. Like multiple sensors will be able to transmit at the same time. It is the responsibility of the server to decode. Okay, so the data that will be transmitted will be overlapping. It is like CDMA. You can assume it like a CDMA. And the spreading factor will be different for each sensor. Based on the spreading factor, the LoRa gateway or the network server will be able to separate or decode the data sent by the sensors. It supports up to 15 kilometers, and it gives you very good battery lifetime. And this is the architecture of the LoRa. The LoRa gate, it is proprietary, it is not, but it runs in license-free band. There are many networks, many gateways already, it covers India. The LoRa network covers India. So if you buy LoRa gateway, like depending on your the cost, like if it is distance, you can purchase the LoRa gateway, and you can connect the end devices, the microcontrollers with the LoRa gateway. And gateway is in turn connected to the network server. As I said, different spreading factors are assigned to the end devices by the gateway. And the network server will be decoding the data, and network server is normally connected to the internet using TCP/IP interface, right? But here the interface is entirely different, right? Between the gateway and the end device, and between gateway and network server, the interface used is it is not a normal TCP/IP. It has its own protocol stack. But from the network server to the internet or to the cloud, TCP/IP can be used, right? So this is the architecture of LoRa, and it covers up to 15 kilometers. And this is the status of LoRa network. It covers most of the countries, and India is also almost covered. We have another technology called RPMA, which gives very huge range, but it is that support is not there in India. And there is a smart, there is a case study for LoRa in smart agriculture. Like if you consider this land, it is mainly for monitoring cattle and for monitoring the water level in the ponds, which is used by which is consumed by the cattle, by the cows here. Okay, so we have a LoRa enabled transceiver in the collar of all the cows here, or the cattle, and then the water quality and then the water level can be measured using a water quality sensor. So it is implemented for a very large area of 7 kilometers, and there is a fixed stationary receiver, okay, with internet connection. Like this LoRa gateway is, it is installed in the drone. Like the drone has to take off from here, and landing should also be done near the stationary receiver. The LoRa gateway is going to just fly and collect the data frequently from all the LoRa transceivers. So now we can say the infrastructure itself is mobile here, since it is kept in the drone, right? It is not that we have to, because the LoRa gateway can be battery operated, even the other gateways can be battery operated. So it could be kept in the drone, and it is just collecting the data across the entire land, and it lands here. And here it is just all the data which is stored in the LoRa gateway is transmitted to the stationary receiver, which is connected to the internet. So this is one application of LoRa in cattle monitoring. And for water quality monitoring, there are many sensors available: electric conductivity sensor, pH sensor, turbidity sensor, ultrasonic sensor. All these are kept in this box that we saw here, which is for measuring the water quality. Because it cannot be floating on the water. Radio frequency does not work underwater, right? So it needs to be kept near the pond, or the water pond, and it is for monitoring the quality of the water, and also for the water level. Okay, and these are all the components which is present in the water quality sensor module. It is battery operated again, and solar panel is also kept. You can observe here. The solar panel generates energy and powers up the controller, and the backup battery is also present, and like it has LoRa LoRa module, right? LoRa end device module is present in the water quality sensor. And as I said, it is implemented in Malaysia, which is of 7 kilometer long. This 3,500 acres with 7 kilometer long, right? And here this red square indicates the transceiver, fixed transceiver, and yellow line is the cattle, and the star indicates the water sensors. This huge land is monitored here. And the next one is data storage and data analysis, the last part of the IoT architecture. Till now, we have seen what is there in the perception layer and what are the protocols in the transmission layer and how it could be connected. And like whatever the data collected from the sensor, it needs to be stored in the database. So the database could be either relational database or a non-relational database. and it can be directly connected with the edge device, right? Or it can be connected with the network which is present in the near the land, or it could be in the cloud as one of the device in the storage area network. And like if we see traditional databases, like it may fail because of the bottleneck issue. So normally people go for distributed data storage, and like blockchain is the recent trend. Like it is like the information can be stored in a decentralized manner, and trusting is also like ensured here when we use blockchain. So this is about the data storage for the IoT. And data analysis. We know the data analysis could be either a classification based algorithm which is running in the edge server, or it could be a machine learning algorithm, or a deep learning algorithm. If it is on, if it deals with real time video, then it could be a deep learning model. But no, we need to keep one thing in mind, like the Raspberry Pi or the Arduino cannot run a deep learning model, or it can run a simple classification algorithm, but it is difficult to run a machine learning or a deep learning model in a normal Raspberry Pi. But we have artificial intelligence board like Jetson Nano, Jetson TX2 boards can be kept as the as a board or as a microcontroller device in the drone, and it can have a model. It is just, it has GPU instead of microprocessor or microcontroller. It has GPU, so it will be able to just monitor the the crop images, and the video can be captured. Even the potholes, all these can be captured. Wherever the real-time video has to be monitored, we can go for artificial intelligence based board. Otherwise, like we need to keep on sending the images. Like if you capture the real-time images from the agriculture land, then it needs to be sent to the edge server from your Raspberry Pi. The processing cannot be done in the Raspberry Pi board, right? And again, the computing could be done either, the model could be executed either in the cloud server or edge server. It is always better to run the model in the edge server instead of the cloud server. Edge acts as the backbone for the cloud, right? Because if all the data which is collected from the big data, no, it will take, the latency will be more, and the amount of data is very high. It is huge. Instead of transmitting the raw data to the cloud, you can just process the data in the edge, and the processed data could be sent to the cloud. So these are all the data analytics points with respect to the IoT. And again, like you can just look at the diagram. And when we use edge computing, the amount of data that is sent to the cloud is going to can do the long-term analytics. Because if the analytics is based on the past data also, then you need to send it to the cloud. And then the cloud is responsible for controlling the actuators of the agriculture. Especially the actuators are very much used in like the facility agriculture and the order agriculture than precision agriculture, right? So in that case, like it is better to have edge computing, that is IoT level 6. As we discussed, there are many levels in IoT. IoT level 6 is suitable for this kind of hybrid scenario. Okay, then security challenges in agricultural production. See, the disadvantage or the very big challenge in agriculture 4.0 is the security. Since the data has to be communicated over the wireless medium, it can be hacked, and the IoT is low in terms of power and computing. Like executing a very strong encryption algorithm in the edge sensor may be very, very difficult, right? The processing is needed, high processing power is needed for executing a very strong encryption algorithm. So in that case, there can be a lot of issues in the smart agriculture also. For example, harsh environment. See, assume, we do remember the locust attack which happened in 2019, right? because of the insects. Suddenly, locust was attacking huge, the lands. Right, it was a very great loss for the farmers. In that case, the solar pump, the solar lamp could be used, which will be discharging very high voltage pulses. Like the current will be triggered by the solar lamp, SIL lamp. It is called solar lamp, right? So in that case, no, since it operates on 6,000 voltage for killing those pest, migratory birds, this would be helpful. But the problem is the interference may happen when it is used in the agriculture. For example, assume you are collecting the sensor data through the Zigbee protocol, right? When we have a very harsh environment like this, the interference may happen because of the electricity, the high voltage. So if the Zigbee sender or the receiver is very close to the equipment, that is the solar lamp, then it will be affecting. There will be a very high interference. We will not be send the data during that particular time. Okay, so that should be considered. If the distance is less than 10 centimeter, definitely there was a study conducted. So it affects the sensors. It means the interference happens in the Zigbee received data. Okay, so that is one security. That is, and sometimes the sensors which are kept in the agriculture land, it gets stolen. That is also a security problem. Then data tampering and interception. Hackers may tamper the data. No, when they try to tamper the data, like it changes the accuracy of the model, we can say, right? When they tamper the data, they mine the data, and it leads to strong the privacy issue, right? So we should ensure that very complex encryption algorithms are executed, but it is very difficult to run very complex encryption algorithms in a very small sensor. Then facility damage, like a facility damage is like because of failure in some link or failure in the sensor, the data may not reach the edge server or the cloud server. During that time, the diagnosis or the prediction may be wrong. Okay, that is another the facility damage that could happen in the sensors, right? While using sensors. And these faults can be detected actually when there are errors or fault in the facility. It should be immediately detected by the neighboring nodes, and then there should be corrective measures taken for that. That should be ensured in here. And because of the facility damage, what can happen is when the data gets missing because of the link fault or the sensor fault, there could be uneven spraying, because since this sensor data does not reach the end device, if it is not corrected, if it is not noticed, then no, it leads to uneven spraying. That is the model. The analytics assumes that there is a huge amount of spraying or pesticides required here, then it leads to uneven spraying. Okay, so that could be one thing. And malicious data attack. So again, like if the data does not reach, for example, assume there are locusts here, but it is not reaching the cloud. The data in the database, the data is removed, or it is like it is modified by the hackers. In that case, the solar lamp may not operate to kill the migratory birds during that time, right? So that becomes a problem here. And like the control system intrusion may happen. The intruders may operate the devices wrongly, right? The actuators can be operated wrongly by the intruders. So now if you see one of the device goes in a wrong direction, all these can happen. So we have to make sure that the privacy and confidentiality and authentication algorithms should be running even in the end devices. But again, it is a challenge. There should be a balance between these two, right? And this is about the security challenges in the IoT smart agriculture. And this is the work that is being done by like me. We got funded by VIT, and we are doing a project where the pest animals, we have considered only monkeys, because in Tamil Nadu we have no huge profit and loss because of monkeys damaging the agriculture crops. So it should be, and nowadays, no, these monkeys are repelled away manually. When the farmers are looking at the monkeys, they use calcium carbide cannon or firecrackers for creating noise, louder noise, and so that it disperses away from the field. It is done manually. Still, it is a very big problem even in north states, right? So, in order to overcome this, we try to automate the detection of monkeys using a deep learning model, which will be running in the edge server. And while detecting monkeys in the field, like we try to use ultrasonic sensors and uh, uh, the cameras. But now we are using Wi-Fi because of the unavailability of Wi-Fi halo. There are two layers formed. The outer layer is ultrasonic, that is the motion sensors, and the inner layer is the cameras. So when the monkeys are detected, and we assume it to be rotating cameras, and when the pest is not covered by the camera, these motion sensors will be helpful. There will be no cure. The protocol, the Wi-Fi access point will be receiving data from the motion sensors and also from the camera. And the captured images are sent to the edge server. Edge server will be responsible for detecting the monkey, whether it is monkey or some other human. That will be detected, and accordingly, the calcium carbide cannon will be automatically triggered towards the direction of the pest animal. This is the project that we are currently implementing in our VIT Chennai. Myself, along with a mechanical faculty member, we are executing this. So here the disadvantage is that we have to use Wi-Fi, because we have to make sure that it always is, all the cameras are powered. The microcontrollers connected with the camera is powered, and all the time it has to capture the image. And otherwise, no, it will be very difficult. And we are trying to apply some intelligence when we have Halo, Wi-Fi Halo enabled in our place. Then we will be able to use them. Based on there should be a little amount of intelligence incorporated in these four microcontrollers, and based on the intelligence, it will be capturing the image and then sending it to the edge server occasionally, not all the time. So this is what the research work that is going on. And I acknowledge all these papers. I referred all these papers, and I have taken contents from all these research papers for presenting this seminar. I acknowledge all these authors. Yeah. Thank you very much for the patient listening. Are there any queries?
Yeah, participants, if you have any queries, kindly raise your hand. We will unmute you. Or you can put in the chat box. Sandeep, can you unmute Prasad, sir? Yes, sir. You can speak, sir.
Oh, okay. Am I audible, ma'am, now? Hello?
Yes, sir. You are audible.
Okay. A very nice presentation, madam. So, I want to learn something from this presentation, that you have mentioned about the major nutrient sensor, what is nitrogen, phosphorus, and potassium.
Yes.
So, from where it is available, ma'am, sensors, how it measures NPK?
Sir, actually, now there are two ways possible. One is the NPK values, the laboratory-based electrochemical sensors are available,
Okay.
which will be used for detecting the value of NPK. It is available in the markets.
Oh, that NPK sensors, which
Yeah,
component?
NPK sensors. It is for measuring the soil nutrients. It is available in the market. You can just search as NPK sensors.
Okay, madam. That is another two terminology you have used. I am not understanding properly. That low bite rate and
Yeah.
relaxed latency. Can you
Yes.
please explain?
Yeah. Sir, all IoT devices are low IoT communication protocol supports only less data rate, low bit rate. Because since we are interested in sending the sensor data to the internet, right? So this data is small in size. So only low bit rate is enough for IoT. We don't need very high data rate like our internet, right? We need only very less data rate for IoT based sensors. And latency is also not very much important here. Like it is not a very time critical like within few milliseconds we do not want to take action, or we do not want to take control the actuators, right? We have sufficient time, so low latency protocols. It means no, the sensors will be allocating it will be the space or the channel will be scheduled by the gateway, right? So most of the time the sensors will be sleeping, and it gets whenever it gets the medium, it transmits data. It is not continuous data transfer like our normal internet.
Okay, that one. And one request, ma'am, if you provide the full form of those, because I am not knowing, some full forms are there and some full forms are not in PPT. If you provide, it will be helpful for us.
Yeah, sure, sir. Sure.
Okay, thank you, ma'am.
Thank you, sir.
Any other questions from the participants? Okay. If there are no questions, thank you, ma'am, for the wonderful presentation.
Thank you, ma'am.
Yeah.
Thank you very much for the opportunity given to me for presenting my ideas. Thank you very much, Rika, ma'am.
Ma'am, 2 minutes. We will. Yeah. It is a token of appreciation from our side for coming and taking the, enlightening the participants here on IoT architecture. Kindly accept. And there
Thank
is a
you. Thank you very much.
Yeah, there is a certificate also.
Yeah. Sure.
Thank you so much for your valuable lecture. Now I request Rama sir to give a vote of thanks. Sir.
Yes, ma'am. Good evening, everyone. On behalf of ATAL AICTE FDP and KL University Hyderabad, we are very much grateful and thankful to Dr. Radha Madam, Associate Professor, School of Computer Science and Engineering, VIT Chennai, for giving a fabulous lecture on IoT-driven agriculture. Ma'am, it is an excellent lecture. You have covered a lot of information and given a lot of information within a span of 2 hours.
Thank
you. It's a great lecture. Thank you once again, ma'am, for giving a fabulous lecture. Thank you, ma'am.
Thank you.
Thank you, ma'am. And participants, the assessment link will be shared in WhatsApp. I kindly request you all to complete the assessment. The link will be open from 9 to 9:30. From next week, we will start with the offline sessions. In the offline sessions, the first day we'll have a field trip wherein we need to concentrate on the reflection journals.
And I expect all participants to write the assessment test. The link will be open now, and it will be available for half an hour. That is from 9 to 9:30. The link will be available. You can open the link and start writing the answer. At 9:30, the link will get closed.
Yeah. And Monday, I request all the participants to attend offline session at KLH campus. Bus facility is provided for the participants who have requested for. We will be sharing the document and the bus in charges numbers so that you don't have any glitches while boarding the bus. And we also request you that on the first day we have a field trip where the scientists will explain you the different aspects of agriculture that is going on at IIOR. So kindly don't miss this opportunity. Kindly connect us on Monday so that Monday entire half a day we will have a field trip. You can directly connect with the scientist and you can explore and get back good tie-ups. What I hope is with the scientists there in IIOR. Thank you so much. Sir, shall we end up the session?
Once again, and all participants, please be in the campus at 8:30 a.m.
By 8:30. Those who are boarding the bus, they can board the bus. They will be into campus by 8. Okay.
Yes.
Thank you so much for being here for the first 1 week, and we hope your participation for the next coming week also. And we ensure that at least by the end of the 2-week FDP, participants will go with a good journal submissions. So kindly be with us for the upcoming week. Thank you so much and have a very good weekend. Thank you. Thank you, sir. Sandeep, can we close the session?
Ma'am, Rekha ma'am?
Yes, sir.
Bus details shall we share here or we will put it in the WhatsApp group?
We will put in the WhatsApp group. Let them.
Okay.
Yeah. Okay, sir. We'll close the session. Okay.
Thank you.
Right.
Thank you.
Right.